alone, 8.75 million people were diagnosed with type 1 diabetes, and 1.52 million among them were under 20 years old. Additionally, over 500,000 cases emerge annually. A continuous blood glucose monitor is a big part of their lives, and the current design uses a filament which is inserted into the skin to measure glucose levels in the interstitial fluid. However, this design has seemed to cause rashes, allergies, bleeding, and cold sores. Users have also asked for sensors with a longer lifespan so that they don't have to replace it so frequently. Hence, we decided to come up with our own design, Glucosense. It utilizes sliding-based triboelectric nanogenerators, which converts mechanical energy to electrical energy, thereby supplementing the battery life of the sensor. We tested this using a physical prototype which generated VC output through sliding motion of paper.
Keeping in mind the need for long-term power generation, the parallel sliding model was considered as it offers more freedom for movement and a consistent electric field due to its uniform electrode alignment. Ultimately, to maximize charge transfer and contact, this was adapted into a staggered electrode design. This ensures consistent contact due to its flexibility by design. Staggering the different electrical sections to make contact at different times, this ensures continuous charge transfer and a more efficient charge collection and separation process. With regard to the materials chosen, there is a need to maximize the difference in triboelectric affinity to maximize charge transfer. They also need to be cost-efficient, flexible, sturdy, and durable, which is why PTFA and PA nylon were strong contenders. To maximize movement between the electrodes, microsprings that trigger consistent movement were integrated into the design. These amplify the sliding movement and ensure layers move along the muscle gradient easily and are sensitive to any movement. The output from this tang is then sent into a Bennett's doubler circuit to amplify it into a DC output, which is then used to charge a supercapacitor via a charging chip, which will help to store energy during inactive periods. Supercapacitors are better than long-term power storage systems like batteries because they minimize heat loss, have a higher power density, and can charge very quickly. This output is sent through a low dropout regulator, which provides a stable output to the RF430 chip, which is responsible for glucose calculations based on the current generated at the electrode connected to the microneedle sensors, and an EM9304, which is responsible for Bluetooth transmission of these results to a connected app for continuous monitoring. Our integrated CGM is an L-shaped device which will be placed on one's thigh. The tang section is placed along the quadricep muscle, which will regularly contract and relax during movement. The elongated tang patch design is intended to maximize the conversion of the steering force into electrical energy. To increase user comfort, this device is the size of a Dexcom G6 and is relatively thinner than other monitors on the market. Ultimately, Glucosense is a cost-effective, long-lasting, painless, and sustainable solution. So join us as we revolutionize the CGM market.